Today we're going to talk about how physical and chemical properties can be predicted using the periodic table. Let's start by talking about what a physical property actually is. A physical property is a property that can be tested without changing the type of matter that you have. In other words, it's a property that can be tested without doing a chemical reaction. So the chemical composition of the material will remain the same. For example, you can test the boiling point of water by boiling it. It stays H2O the whole entire time. Some common physical properties that we talk about are boiling point, melting point, density. Other things we can measure are things like color. We can observe color, we can look at things like that, but these are some of the big ones that the periodic table allows us to predict. Along with boiling point and melting point, I'm also going to add to this phase of matter at STP, which is related to boiling point and melting point. That's what actually predicts that. So the main physical properties that we're going to be looking at on the periodic table are going to be, in terms of predictions, are going to be melting point, boiling point, and density. Just to pick one to focus on, I went to reference table S, and I filled in boiling points up to argon. What you're going to notice, hydrogen's kind of a weirdo, so hydrogen's got this really weird low number up here. Everything else over on that left-hand side is pretty high. These are Kelvin boiling points. Those are very high temperatures. As you go across the periodic table, you're going to notice once you get into the nonmetals, you get into this section of much lower boiling points, okay? So based on this, you could make a prediction. If you were looking, for example, at group 18, what would you predict that your boiling point for element 36 might be? So if you were like, okay, well, argon's boiling point is 87. Looking down this row, they are going up, but they're still fairly low numbers. So you might be able to say, okay, I bet krypton would have a boiling point of maybe something around, 100 Kelvin or so, something like that, which sounds pretty reasonable. If you then go and look up krypton, its boiling point is actually 120 Kelvin. So that kind of is pretty predictable there. There isn't really a mathematical relationship you can use to calculate the exact boiling point, but if I told you that krypton's boiling point was 2000 Kelvin, based on this trend, you could pretty much call me crazy. So a trend that I'm going to notice in boiling point is that the higher ones are on the left, and they drop as they go across the periodic table. Gallium's another prediction that we could make. So if I went and looked at gallium, keep in mind gallium is number 31. So gallium is right here. If I wanted to make a prediction about gallium's boiling point, it's a little bit tricky based on some of the other numbers that I have, but you'd probably make a prediction that it would be somewhere around, I would say maybe 3,000 or so, 2,000 to 3,000. Based on the ones that are around it. Gallium's actual boiling point is 2,477 Kelvin. So again, it's not perfect. You're not going to be able to predict an exact number necessarily. It's not something you can calculate to get an exact value, but you can actually come up with a prediction that's fairly reasonable. The periodic table will also help us predict how elements will bond. Bonding is a chemical property. So two important ideas we're going to talk about are electronegativity, which is how well an atom holds or attracts electrons. I like to think of this as the idea of strength versus ionization energy, the amount of energy needed to take an electron away from an atom. So ionization energy is actually a quantized amount of energy, meaning it's actually measured. Electronegativity is actually a comparative scale. It's a little bit easier to look at the numbers on it, but these two ideas talk about the same thing. How well does an atom hold electrons? If an atom holds electrons really well, it's going to bond by gaining electrons or maybe sharing them. If an atom does not hold electrons very well, it's going to bond by losing electrons, which is what happens with metals. So this is important because it's going to help us predict if cations or anions will form, or if electrons maybe in some cases in bonding will be shared, which we'll talk about a little bit more in our bonding unit. These are both findable on reference table S. And if you're looking at reference table S, you're going to notice when you look at electronegativities, electronegativities actually do not have a unit given with them. The reason for this is an arbitrary scale made up by a guy called Pauling that allows us to compare how well different atoms hold on to electrons without actually giving a very specific measured amount for that. Ionization energy, on the other hand, is in kilojoules, which is an amount of energy per mole. Both of these generally tell us the same thing, though, how well atoms hold on to electrons. So these are going to help us to predict bonding because elements with low electronegativities will lose electrons and form cations or positive ions. And these are the elements on the left side of the periodic table, or the metals. On the other side of the periodic table, when we have our elements with high electronegativities, these are going to be elements that gain electrons. Sometimes they might also bond by sharing electrons, which we'll talk about more in the next unit. We've talked more at this point about ions, so I'm kind of sticking to that description. But what this will predict for us is that elements that are nonmetals, which have these high electronegativities, don't bond by losing electrons. They either gain them or they share them. You're also going to notice there's a correlation between electronegativity and ionization energy. If an element has a high electronegativity, it has a high ionization energy. So I filled in some electronegativities. These are really easy numbers to look at since they're just right out of 4.0. They only have one decimal place, kind of like a grade point average in college. What you'll notice as you look at table S is when Pauling made his scale, he took the noble gases right out. So he said, hey, I want my scale to be focused on bonding, so I'm not going to really compare this to elements that don't typically bond. So if you're looking at your scale, the highest value you can have is a 4.0, which fluorine actually does have, so we actually do have the highest value on the scale over here. The lowest value out of those I've shown you the lowest value that you can see over here is sodium. So again, you can technically go down to 0. I can't think of any elements that actually have 0 as their electronegativity, but this gives you a pretty good idea that if you bond something with oxygen or fluorine or chlorine, for example, that they're going to form negative ions by gaining electrons. So the elements that have low electronegativities are going to be our non-metal, or I'm sorry, are going to be our metals. Elements on the left side of the periodic table. Those that have high electronegativities are going to be our nonmetals. And again, he left off the noble gases. This just sort of makes the scale a little bit more doable because the noble gases are extremely good at holding electrons, but we don't need to really worry about them in terms of bonding.